Hi everyone, this is BitRocket. My name's Andre. Today we're taking a detailed look at our 20-foot hydro container, designed for 210 Antminer S23 Hydro units, equipped with a closed-loop wet cooling tower. This one is adapted to Russian climatic conditions and electrical networks. We'll talk in detail about each module, and I will show you everything. Let's go. So, let's start with the entrance group. The first difference from air cooling containers is the status light column, which visually indicates the status of the container. It could be stopped, standby, ready to start, starting, running, emergency stop, and so on. The advantage of this column is that when you have a large hosting facility with 10 or 20 containers, you can see the status of each of them simply by looking at the column without having to go and check each of them individually. Next, these are ventilation grills. By default, they are located along the racks and are blown by an exhaust fan, removing residual heat from the container body. Another special feature is that there are two stop buttons here, for the left and right switch gears. Since we have two independent inputs and one pump group, there are certain difficulties in synchronizing the power cabinets. So we had to make two buttons here, since the galvanic isolation of these systems is very important. If you have an emergency, you just press the two buttons, the switchgear turns off, and you're fine. By default, in the place of the cable input, we have a switchgear. That is, the cable goes directly from below into the switchgear to the input circuit breakers. We use 630 amp breakers. The total power capacity of 1.2 megawatts is divided into 4 separate inputs, so that you can connect it into any standard transformer substation. Unlike some competitors, we avoid using 2000 amp breakers, which can complicate installation and connectivity. We have standard cables of about 185 millimeters squared. The 4 inputs are synchronized with each other, so if an accident happens, we can shut them down synchronously so that the pump does not shut down with the miners left running without a coolant flow. Connection of the cooling tower. The main units holding the pipelines are these elevated supports, or as we call them, trestles. The pipes are supported by specifically manufactured height-adjustable suspensions. Here you can see the threading. We use custom-made enlarged studs. Any minor elevation differences at the location can be easily compensated. Vibration dampers are installed both at the point where pipes enter the container and at the cooling tower connection. The system completely dampens vibrations and compensates for thermal expansion. The cooling tower has an irrigation pump, which delivers water from the basin into the irrigation system at the top. The makeup valve. In automatic mode, the controller reads level sensor data and decides when to open the valve for water replenishment. The water passes through a chemical water treatment system. It's currently removed for filming. Overflow system. Here you can collect a polyethylene adapter to safely drain excess water in case of malfunction. For example, if the makeup valve keeps filling the system. And the drainage control system is crucial for winter operation. If, for example, you didn't fully winterize the cooling tower, the system will switch to emergency mode and drain the remaining water. It's also used for regular water replacement, since water gradually accumulates dust, insects, and impurities over time. In order to change the water over time, you can set a schedule for the system to periodically drain and refill itself, keeping the water fresh in automatic mode. Next is the tray temperature sensor, which controls the drainage protection. In general, you can monitor the temperature of the water in the tray and the temperature of the irrigation water. Here you can directly observe the evaporation point, which is the water that comes out of the shower and rises into the air. This sensor shows the evaporation point, an important point when connecting the cooling tower to the container. There are 3 types of connections. One is a loose flange. It includes a flange ring with a lip and a freely rotating backing flange. You first align the flanges center the gasket, and then tighten the bolts. The second connection is a rigid flange. It is similar in function, but here the flanges are already perfectly aligned. You only need to center the gasket before tightening. Then you tighten the bolts crosswise, gradually increasing the torque. The third and most critical type of connection is the vibration dampers. You can see them both at the container and at the cooling tower connections. These connections are done in 3 stages. First, you pre-tighten the bolts to about 30 Newton meters. Then you wait 15 minutes. Next, you increase the torque to 50 Newton meters, and the final tightening is at 80 Newton meters. The required torque varies depending on the bolt diameter, so you'll need a torque wrench suitable for different sizes. If we come to your site for commissioning and setup, we'll bring all the necessary tools. The third module is the chemical water treatment system, located at the end of the cooling tower. Its main purpose is to chemically treat and purify the water used in the cooling tower. How it works. First, you order a water analysis based on the following parameters: pH, total hardness, calcium, alkalinity, electrical conductivity, or total dissolved solids, iron, sulfates, and silica compounds. Once you receive the chemical analysis report, our chemist selects the appropriate chemical reagents to neutralize harmful components. Now, how does the system operate in practice? The reagents are poured into drums. Inside each drum, there is a float valve controlled by the system's controller. And here are flow meters with pulse signals installed. When the cooling tower starts to lose water, it sends a signal to begin refilling. The flow meter detects the volume and sends a signal to the controller indicating exactly how much water is entering the system. Each controller is provided with the information from our chemist, so it knows how much of each reagent should be injected per liter of incoming water. The controller activates the dosing pumps to inject the correct amount of chemicals. This treated water then flows into the cooling tower. So, to reiterate, before we design your system, we always require a water analysis to ensure long system life. Now, let's look at the main components inside the container. Each rack is served by 7 manifolds for supply and return, with 15 miners in each. That's 105 miners on each side. Switchgears. Switchgear 1 and 2, each powering one half of the container. The automation cabinet can connect to either of the switchgears, so it doesn't matter from which side power is supplied. This is especially useful when powering the container from generators, as you can run only half the container. The pump unit. The pump unit includes the main pump, piping and valve assembly, check valves, shutoff valves, sensor systems, vibration dampers, flow meter, and, which is very important, the derator. It removes air bubbles from the coolant and we release them. Next, we have a 60 kilowatt boiler for heating. Before starting up, the system must be heated to the startup temperature, 22 degrees Celsius. We turn on the boiler and use a separate pump on a dedicated loop to gradually heat the entire system. Then we can start the miners. Here is the top-up tank, the top-up pump, a fan for climate control, the network system, which we will discuss separately. Here is the expansion tank, which absorbs pressure surges. The first element is the top-up tank. Here's how it works. We fill the system with ethylene glycol from an external source. For this, we have a filler neck outside the container. Also, there is an electrical outlet outside controlled by the system for powering the pump that will do the filling. You bring a drum up to the container, connect it, turn on the pump, and activate the automatic filling mode. Using level sensors, the pump fills the tank until it reaches the upper level, then stops. As the system consumes fluid during operation, the level drops and the pump automatically refills the tank. Next is the top-up pump, MO2. When switched to automatic mode, it begins pumping fluid into the system. It stops when the level in the tank drops to the minimum threshold. As soon as the external pump refills the tank, the top-up pump restarts automatically. This pump operates in 2 modes, the filling mode and the pressure maintenance mode. In case during the operation the temperature drops or rises, It works together with the safety relief valve. Its main task is to keep the system pressure within a set range, typically between 1.5 and 2 bar, depending on the specific configuration. The next component is the durator. The durator is installed at the pump inlet. This is the return line. It comes in before the pump, enters the durator, and only then goes into the pump. The durator's purpose is to remove air bubbles from the coolant. If these bubbles aren't removed, they get into the pump, where they break into even smaller micro bubbles. Gradually, the liquid becomes foamy. The durator's job is to slow down the fluid flow and separate the air bubbles. As you can see here, the bubbles have collected at the top. We can manually vent them from time to time. Air from various parts of the system gradually accumulates in the durator, so you can manually remove it. The tank itself has a 300-liter capacity. It has minimum and normal level markers, designed so that the volume of ethylene glycol, about 2 tons in the system, can safely expand when temperatures change from minus 30 degrees Celsius to 50 degrees Celsius. So, if the 2 tons of ethylene glycol expand, there's enough space for it. Excess fluid will return into the tank through the relief valve. Now, the boiler. Its purpose is to heat the system to the startup temperature. By default, this is set to 22 degrees Celsius. In a custom setup, you can lower it slightly, but still, if it's below or around 0 degrees outside, you won't be able to start. This boiler is our own design. It has 4 heating elements welded into the tank, each one 15 kilowatts. They can be divided into groups. So if it's not very cold outside, you can use only half of them. It is fully controlled by the automation system via separate circuit breakers and contactors. It has a dedicated pump and a separate loop. That's why we have a check valve installed on the pump group. The boiler pump connects into the upper part right after the check valve to prevent backflow. Once activated, this loop circulates and heats the entire circuit evenly. Every critical component in the system is duplicated with pressure and temperature gauges. This pipe here is the return line from the miners. So it carries hot water going into the flow meter and the durator. We see temperature sensor, thermometer, pressure sensor, and pressure gauge. During commissioning, without even looking at the monitor, we can quickly check the pressure and temperature on site. Right now, the pressure is 1.2 atmosphere. The main component of the pump group is the circulation pump. Its key feature is that it's selected with a 20% safety margin, not only in flow rate, but also in head pressure. Antminers have high hydraulic resistance, and very often there are issues where you can't push the required amount of water. The manufacturer recommends 10 to 11 liters per minute through the 10mm tube or the compression fitting. This pump, thanks to its high head pressure and optimized impeller design, can deliver the necessary flow with reserve capacity. It can operate in a nominal mode, not at maximum load, which increases its lifespan. The next component is the manifold system. One manifold supplies liquid to 15 miners. Pay attention. The supply and return lines are located underneath the miners, arranged in a specific way. The supply line is on the right side, and the return line is on the left. Due to hydraulic resistance and pressure difference, this setup ensures that each miner receives equal cooling. If the supply pressure here were 3 bar and the return were 1 bar, the miners at the ends would have uneven pressure. But in our design, the pressure differential remains consistent across all units, so the flow rate through each miner is uniform. I'd like to note that we manufacture our own power cables. We take the plug and run the cable directly to the circuit breaker. Each cable is clearly labeled, and every Ethernet cable is also labeled. Also, all valves and compression fittings are made entirely of stainless steel, so there's absolutely no risk of chemical reactions. Finally, let's finish with the manifold system and how water reaches it. The main 129mm pipe runs to this point, then a T is installed. Then we have 100mm disc valves, So we transition to a 100 millimeter pipe, then a 100 millimeter vibration damper. After that, we have the 100 millimeter manifold. From that manifold, through clamp adapters and another vibration damper, that compensates for expansion. We connect to the individual minor manifolds. That's roughly how it works. We would like to present for review our own in-house manufactured cabinets. A brief backstory. Due to the extremely tight component layout inside Hydro containers, we often work with just centimeters of clearance, carefully fitting each unit into its place. For example, this switchgear cabinet is 800 millimeters wide, and the automation cabinet is 700 millimeters wide. A larger cabinet simply wouldn't fit. We realized early on that using standard server racks would not always be practical, since we can't adjust them to suit our needs. That's why we developed our own frame system, along with a custom mounting structure, doors, handles, hinges, locks, and all related hardware. Now we can manufacture cabinets not only for containers, but also for indoor installations of any required dimensions. For instance, this cabinet, which is 2.3 meters in height, can be made as a standard 2-meter version, or whatever the project requires. Now, let's go over each cabinet separately. First, the switchgear cabinet. It features an emergency stop button. If you're inside the container and there's an emergency, pressing this button immediately triggers 2 independent trip units, cutting power to this switchgear. And you can also disconnect the other one. Next are the power meters. In our Hydro systems and Hydro containers, we've switched to power meters produced by Chint. These support the Modbus protocol, so all data collected, voltage, current, phase readings, power factor, is transmitted directly to the controller. There, everything is summed up and used to calculate the container's total power consumption. Next, the switchgear is composed of 2 input groups, 2 main circuit breakers. The protection scheme uses independent trip units. We monitor for overvoltage, undervoltage, phase loss, neutral loss, and phase imbalance. In addition, the system can also be disconnected via the button on the cabinet, the emergency button on the container itself, or remotely through the controller. You can shut it down from the SCADA system, from a cloud service, or directly from the local touchscreen, depending on your situation and why a shutdown is necessary. Each miner has its own 3-pole circuit breaker, and all breakers are clearly numbered. So if you need to service a unit, you close the valves, turn off the miner, and switch off the corresponding breaker. There are also feeder breakers, rated at 160 amps for frequency drives, heaters, and other components. That covers the switchgear cabinet. We can move on. The automation cabinet's main component is the automatic transfer switch. Its primary function is to switch between the first and second power input. This allows you to power only half the container. Next is the power distribution block, where we distribute the power supply to the frequency drives and to the automation board. The automation board itself is a complex unit. Here's the essence. The controller is powered independently from 2 separate inputs coming from 2 different cabinets. No matter which power source is active, the controller always remains powered. We have a separate power supply unit for the valves. All control circuits are galvanically isolated using relays. This includes frequency drives, valves, pumps, and so on. All terminal blocks are installed according to the circuit diagram. For controlling contactors, we use bistable relays. They are triggered by a pulse signal to switch the contactor state. Our network is built on micro-tick equipment with 2 internet inputs, primary and backup, which then distribute to Cisco switches. Now, the main control element in the automation cabinet is the rotary selector switch. It has 3 positions, corresponding to 3 main operating modes. The first one is stopped. In any mode, you can switch to stopped, which immediately breaks the power circuits to the frequency drives, shutting everything down. The second position is local mode. When switched to local, you control the container directly from the site, using the display, buttons, and other local controls. The third mode is SCADA mode, which enables external control of the container, for example, from a cloud service or a SCADA system. This is useful when you have a large hosting setup with multiple containers. You can integrate this container into a larger SCADA system and remotely start or stop each one from a central control room. Without physically being present at the container, you can start all pumps, apply power, and launch or shut down the entire system. When inside the container, you need to ensure that the operator can't accidentally interfere with the system. For example, if you're working on something and you don't want the container to start up at that moment, you switch it to local mode. If you started the container, left the site, and still need to be able to stop it or adjust some parameters, you switch it to SCADA mode. And then the container can be controlled remotely via an external cloud-based or local service. Next, we have indicator lights that correspond to the light column you've already seen. These show the same statuses: fail or stopped, then standby, which is the current mode. As you can see, we have stable pressure, so the system is in standby mode. The container is ready for startup. And finally, running mode. When the pump reaches the required flow and pressure differential, the system switches to running. At this point, all additional safety protections are activated. This is the main control interface. Here we see the temperature outdoors in the basin, in the cooling tower, in the pipeline pressure, flow rate, which is currently 0, and all power readings and other key parameters. There are many configuration menus available, including PID controllers. For example, here you can see settings for the main pump, cooling tower pump, spray pump, and internal pumps. You can also access tuning parameters. When adjusting a PID controller, you can change values in real time. A detailed instruction manual will be provided with the container upon purchase. One of the key protection systems in this container is overpressure protection. Here's the issue. The pump is selected with a significant safety margin, but within the hydraulic system, the weakest link is the miner itself. The pump is technically capable of generating up to 6.5 bar, a level at which the miners would simply rupture. Therefore, we must carefully monitor discharge pressure. Our first step is routing water through the cooling tower first, where we lose about 0.5 bar. But when the water returns from the cooling tower, it gets to the miners. In order to prevent overpressure, we've implemented a triplicated protection system. We have 3 protection measures. First, we have an electric valve, working in conjunction with the MO2 pump, the system's top-up pump. This valve monitors operating pressure and ensures that the pressure on the discharge line to the miners never exceeds 2 bars. Here's how it works. When you start the system, pressure is at a certain level. In this case, according to the monitor, 1.3 bar. Once the miners are powered on, the system begins to expand. Some pressure is absorbed by the expansion tank, but as pressure continues to rise, the electric valve opens and redirects excess expanded fluid back into the tank. This is the first level of protection, and it operates continuously as pressure increases. Suppose the electric valve fails, or someone accidentally closes the shutoff valve before it, and pressure starts rising to 2.5 or 3 bars. At exactly 3 bars, a mechanical safety valve activates. This is a simple spring-loaded valve with no electronics, and its pipe also goes to the tank. So even if the electronic control fails due to incorrect logic or valve malfunction, the mechanical valve takes over. And if for some reason the mechanical valve fails to open, we have a third level of protection. A pressure relay calibrated to 3.3 bars. Maximum pressure for the miners is 3.5 bars. At 3.3 bars, the relay triggers, which works like pressing the stop button. A signal is sent directly to the independent trip unit, cutting power to the entire container. So this three-tiered protection system ensures stable pressure and makes sure that it's virtually impossible for excessive pressure to reach the miners. Let's add some information about the top-up tank. Two emergency overflow lines enter here, one from the mechanical valve and one from the electric one, both designed to maintain safe system pressure. Next, we see four level sensors: base, minimum, normal, and maximum. The next four pipes come from vertical manifolds. These collect air. This way, when you're filling the system, there's no need to stand around with buckets. Instead, we've connected tubing to standard air vents, linked via compression fittings. So, you slightly open all four valves, start filling the system, and the air bubbles automatically flow back into the tank. There are also several reserve ports in case of unexpected situations, and one of the tubes is connected directly to the derailleur. Let's open the valve. You can see a small amount of air has accumulated. And here we have the filling line. This is where we connect an external pump, which in turn connects to a drum. And this is the overflow neck. You can route this hose to a collection tank or into a drum. If you overfill the system, the excess ethylene glycol will safely drain into a designated container. Now you know how all the system components work. Let's start the system in real time. Get into operational mode. First, we switch the container to local mode. The frequency drives have powered up. Now we go into the settings and start the main pump. We can see that the mode, the system state, has changed to starting. On the trend graph, we can observe the startup process in real time. The white line represents the current signal going to the frequency drive. The red line is the set point. The green line shows the pressure differential between P1 and P2. You can see how the differential is increasing. Now it's at 0.1 and rising. We are creating the required pressure drop across the miners. Look, now we already have flow. We're currently running at approximately, 40%, and already have 50 tons per hour. As you can see here, this valve is also displayed on the screen. 51, 52 tons per hour, continuing to rise. At the same time, notice that the spray pump and cooling tower fans are still off. Why? The system allows startup, since the ambient temperature is currently 16 degrees Celsius, and the pipeline temperature is also low. There is no heat load yet, no miner operation, no heating. So we're not violating any operating conditions. By simply starting the main pump, we can safely transition into running mode. As soon as the miners are turned on and begin generating heat, the spray pump and cooling tower will automatically activate. The system detects this and turns them on independently. Let's go outside and have a look at the light column. We can already hear the liquid flowing through the pipes. As you can see, now that we are outside, the external light column duplicates the same signals as the ones we have inside. Right now, we're observing the pressure differential building up. As soon as the system reaches the set parameter, the target differential, it will switch to running mode. Once the required differential is achieved, we'll see the green indicator light turn on. After we start turning on the miners, the temperature will rise, and the cooling tower system will detect this change and activate the spray pump, then the fans. Using PID control, it will automatically maintain the set point, the temperature of the water returning from the cooling tower to the miners. This is the control target, and the system will maintain that temperature precisely. Now we're building pressure. I'll quickly check inside the container. The current differential is 0.6. So in just a moment, we'll see the transition to green, that is, to running mode. We're not editing this. This is live, one continuous shot. Look, the green light is on. the system is ready. You can now start powering on the miners. The container is fully ready for operation. We've started the cooling tower in manual mode. The indoor temperature is around 16 degrees Celsius. So in automatic mode, the cooling tower doesn't activate at this temperature. Notice that the spray pump is running at minimal speed, and the exhaust fans are also operating at low RPM. Yet the airflow is already quite strong. Cooling in this tower works as follows. Air moves upward, water flows downward, creating a counterflow. This maximizes evaporation and heat loss. The cooled water then transfers its low temperature to the ethylene glycol pipes. That in turn deliver cooled liquid to the miners. This cooling method is extremely efficient, even in hot conditions. While standard systems struggle when ambient temperatures exceed 37 degrees Celsius, our system can operate up to 50 degrees Celsius. Now I'd like to focus specifically on the cooling tower's heat exchanger. The glycol side forms a closed loop made entirely of stainless steel. Hot fluid enters, flows through the coil, gets cooled, and then exits. For the central regions of Russia, we use a 6-row heat exchanger. However, this particular container is destined for southern Russia, so we've equipped it with an 8-row heat exchanger. As a result, the cooling tower is taller and more powerful. This demonstrates our ability to customize cooling towers for any region in the world. We've even performed calculations for Dubai, where temperatures can reach plus 50 degrees Celsius. In such cases, we'd use a 12-row cooling tower, making it about 1 meter higher, ensuring stable and reliable operation in that climate. Our hydro solutions can operate in any climatic zone. The key is proper system design. If you have any technical questions, feel free to send us a message. The links will be in the video description. You're also welcome to visit our production facility to discuss your project or see ongoing installations. We welcome all visitors. Stay tuned. Bye.